Oh, hey there, it's you. Well, I was going to begin my recitation on the whiteboard, but it looks like someone left a wonderful little quote, which gave me pause. Anyways, enough about that. We really do gotta get started on this recitation. Now, I know what you're thinking. It's always recitation this, recitation that. When are we really gonna get to know each other? And you're right. So I figured today we'd begin by me asking how you're feeling. Well, that's nice. Now, me, on the other hand, well, I'll be honest, I've been feeling a little blue. Okay, stop. Enough. No, seriously, stop. Oh yeah, we will also be getting help from someone that I feel knows some of these questions even better than I do. And that's past me. So you won't even notice when past me is talking, as long as you're not paying attention. But every once in a while, he will be talking instead of me. Okay, let's really get started now. So let's talk about the growth of functions. We say that the running time of a function is big O of f of n. We use big O for asymptotic upper bounds, since it bounds the growth of running time from above with large enough input sizes. It's the same as saying our function can't get, our function with respect to running time can't get any worse than this. So we say that the running time of some function f of x is less than or equal to c, which is a constant, times the running time of g of x, when x is greater than k. So k represents how much data we're inputting into our function before it's pairing with c, causes g of x to begin to grow more quickly than f of x. Let's give a specific running time to our functions. Let's say f of x is x squared plus x. In general, we could say that one of the upper bounds of our function is the most quickly growing component of that function. X squared is the most quickly growing component of x squared plus x. So g of x might just be x squared. Now we can see that x squared grows a little less quickly than x squared plus x because x squared plus x has that little plus x at the end there. However, when we multiply g of x times some constant c, then once k reaches the input of our data reaches k or greater, then that function begins to grow as quickly or more quickly than our original function f of x. So then we could say that f of x is big O g of x. We could also say that x squared plus x is big O x cubed, because x cubed is far more quickly growing than x squared plus x, and so it might act as an upper bound. Or big O x factorial. However, we could not say that f of x that we've given here is big O of x, because no matter how much data we put into x, it will never grow more quickly than x squared plus x. Explain what it means for a function to be big O of 1. And simply put, this means it grows at the rate of a constant function. In other words, it doesn't grow. Execution does not depend on the size of the problem. So if we were to graph the running time, it would just be a flat line. No matter how large our data size became, running time would never increase of our function. All right, so now this question is actually two different problems. So let's begin with the first part. Show that 2 to the power of n is big O of 3 to the power of n. And we can do this with a direct proof, and I think it's most easy to visualize if we plot the growth rates on this kind of grid. So on the bottom we have data, and on the y-axis we have time. Now what would the function 2 to the power of n look like? Well, the growth rate would look like this. And compared to 2 to the power of n, what would the growth rate of c times 3 to the power of n look like? That is, big O of 3 to the power of n. Well, it would grow at a faster rate. So clearly 3 to the power of n and also c times 3 to the power of n grows more quickly than 2 to the power of n. So we've shown that 2 to the power of n is big O of 3 to the power of n. So clearly c times 3 to the power of n grows more quickly than 2 to the power of n, right? Regardless of what c might be, as long as c is greater than 0. So we would write 2 to the power of n is big O 3 to the power of n when n is greater than 0. That is to say, as long as we have an input, as long as the amount of input data is greater than 0. And our witnesses would be c of 1, because we only have to multiply 3 to the power of n by 1 for it to already begin to exceed 2 to the power of n. So we know that 2 to the power of n is big O 3 to the power of n because 3 to the power of n times c grows more quickly than 2 to the power of n when c is equal to 1. But we're missing the witness k. We would say k is equal to 0 because 0 is where both of these growth rates intersect at. They intersect at the data point. They intersect when we've input 0 amount of data. What this means is that when data is 0 or greater, at this point, the function c times 3 to the power of n begins to grow as quickly or more quickly than 2 to the power of n. Show that 3 to the power of n is not big O 2 to the power of n. And how do we do something like that? Well, let's set up a proof by contradiction. Let's suppose that 3 to the power of n is less than c times 2 to the power of n. Well, let's do some algebra. What do we get? We get 3 over 2 to the power of n is less than c. And we've already reached a contradiction because 3 over 2 to the power of n is unbounded. Therefore, it can never be less than some constant c. And again, we can plot it. First, let's plot 3 over 2 to the power of n. Do you see the issue here? Well, because this function is growing exponentially, at every data point we input, it's always going to be higher and higher and higher. So it's never going to plateau. And because of that, any constant c we might add, maybe this is c, will always be overtaken by 3 over 2 to the power of n, even if we made c extremely high. At some point, with a large enough input data, 3 over 2 to the power of n would exceed that constant. Therefore, we reached a contradiction which proves the original statement that 3 to the power of n is not big O 2 to the power of n. Let's begin with the first part. Let's ask whether 2 to the power of n plus 1 is big O 2 to the power of n. Well, okay, recall that 2 to the power of n plus 1 is just equal to 2 times 2 to the power of n. Let's take that plus 1 and bring it out to the front and multiply it by the base, right? Remember, that's how exponents work. So we get 2 times 2 to the power of n. Now this matches the big O notation, right? Up here in front, we have our c. And right here, we have the growth rate of the function. For example, f of n. That's c times f of n, which is just big O of f of n, which proves that 2 to the power of n plus 1 is big O of 2 to the power of n when c is equal to 2 and k is equal to 0. Is 2 to the power of 2n big O 2 to the power of n? Okay, let's set up a proof by contradiction. So 2 to the power of 2n is less than or equal to c times 2 to the power of n. So where do we go from here? Well, let's divide both sides by 2 to the power of n. And what do we get? We get 2 to the power of n is less than or equal to c. And at this point, we see that this is absurd, right? Because 2 to the power of n is unbounded. For the same reason as the previous problem, right, where we had something that was unbounded, this is also unbounded, which is a contradiction to our assumption. And what this means for this problem is that 2 to the power of 2 of n is not big O 2 to the power of n. Arrange by increasing big O. We're given a bunch of functions, and I think you should do this one on your own. So pause the video, determine on your own which ones are the slowest in running time and which ones are the most quickest in running time. And then when you're done, unpause the video, and I'll just have the solution available for you. Is this what you put? We can see that 1000 times log of n is the most slowly growing of these functions, because log of n grows very slowly. Just because it's times 1000 doesn't really mean anything, because as input data increases and increases and increases, the 1000 becomes meaningless and the growth rate remains log of n. Next is square root of n, then n times log of n. Then we have n squared over a million. Again, the a million doesn't matter for the same reason the 1000 doesn't matter. The most quickly growing component is the n squared. Next, 2 to the power of n, 3 to the power of n, and 2 times n factorial. Anything factorial is basically the worst or terrible running time of a function, and if you ever wrote an algorithm which was n factorial, I'd probably fire you. Let's show that x squared is big O of x cubed. So to do this, let's use the limit method. So if we call back to calculus, we set up a limit like this. We have the limit where x goes to infinity, and we have something on the numerator and something on the denominator. What goes on the numerator is what we're comparing against the big O, and what goes in the parentheses of the big O goes on the denominator. So we get x squared all over x cubed. Now from there, we can do some simple algebra, divide out the x's. We get the limit from x to infinity of 1 over x. And as x increases and increases and increases, this limit tells us that we're really just saying 1 over infinity. And 1 over infinity gets very, very close to 0. So our final solution is 0. And when our final solution is 0, we're saying that x squared is big O of x cubed. Show that x log x is big O x squared. And then we can do some algebra, take x off the numerator and the denominator. And well, then we're kind of stuck. I'm not really sure how to evaluate it, but well, look, an unknown benefactor left us a clue. Use L'Hopital's rule. Basically, that just means that when we can't evaluate this any further, we can take the derivative of the numerator and the derivative of the denominator to simplify our expression into some intermediate form and make it simpler to evaluate. So, what's the derivative of log of x? Well, it's just 1 over x. And the derivative of x is 1. Show that x squared is big O to the power of x. We begin with our limit. We have no choice but to use L'Hopital's rule. So we say this is equivalent to the limit as x approaches infinity of 2x all over the natural base, or the natural log of 2, times 2 to the power of x. But we're still stuck, so we use L'Hopital's rule again. This is equivalent to the limit x going to infinity of 2 all over the natural log times the natural log, or just natural log of 2 squared, times 2 to the power of x. And from there, I think we're pretty much done, right? A constant divided by pretty much anything with a base to the power of x will get infinitely close to 0, so we say that our solution is 0, and therefore x squared is big O of 2 to the power of x. Show that x squared plus x plus 1 is not big O of x squared. Alright, so again, let's set up a limit. On the numerator, we have x squared plus x plus 1, while on the denominator, we have x squared, which is what's in the big O. So from there, we can split things up, and what do we get? We get the limit as x goes to infinity of x squared over x squared plus the limit as x goes to infinity of x over x squared, and finally plus the same limit as x goes to infinity of 1 over x squared. From here, we can simplify. We see that this is x squared over x squared, which is just 1, and the limit of 1 is just 1 itself. Let's erase this limit here and simply put 1. Now, we also notice here that the limit as x goes to infinity of x over x squared as well as 1 over x squared, both of these will go to 0, or very, very close to 0. So, the limit of these is 0 plus 0. We have the 1 from the beginning, and what are we left with? The final solution is simply 1. And because the final solution is 1 rather than 0, we can affirm the original statement. X squared plus x plus 1 is not big O of x squared. If this were a 0, then this would prove it's big O of x squared, but it's not. It's a 1. Sorry, it's a little dark, but let's determine the big O of the following algorithm, which we wrote last time. So remember, it finds the largest difference between two integers in an array. So how do we determine the big O, just looking at it? Well, all that matters is the loops. So from this for loop to here, we have n minus 1 number of comparisons of the for loop. So our growth rate is bound by the variable n, which is the input size of the array. So that means that big O is n. We wouldn't really say big O of n minus 1 because we're getting rid of the constants, right? That n minus 1 doesn't really matter because the bound is still largely the growth rate of n. Now, just as an exercise, what if we had an outer for loop to this for loop, right? So what if somewhere in our algorithm, we had seen something like this. For j equals 1 to n. And that for loop ends after the inner for loop. So we have a nestled for loop. Well, for every n, we have n number of comparisons. That's n times n. So we have n squared total number of comparisons, which is bound by the input size of the data, n. What this means is because we have two for loops, we multiply them. That's big O of n squared. So that would be the growth rate of this function here. Right, remember a palindrome is a string that reads the same forwards and back. We wrote an algorithm which determines whether an input string is a palindrome or not last time. So what is the big O of that algorithm? Well, we notice that in the outer loop runs for a total of floor n over 2 number of times. That's floor n over 2 number of times. When we're determining big O, we don't regard constants, and we don't regard things like the floor or ceiling functions. So this is simply big O of n. It's big O of n because the number of comparisons within that for loop is bound by the number of iterations of that for loop. So the number of iterations of that for loop are, at the worst case, n over 2 floored. And again, we just drop the constants, and that gives us big O of n. We have that last algorithm we wrote last time. The first term of a sequence of positive integers that is less than the immediately preceding term of the sequence. Again, it doesn't even matter what the algorithm does. We have a while loop, and we have I is less than or equal to n. N is the size of our input data. So the number of comparisons and the number of iterations of that loop are going to be bound by some constant times n, which means big O, again, is simply n. All right, that's a wrap.